Today will be an overview because we are going to talk about the last phase, the project component. Up until now, we have been using the very useful monster as a framework for teaching computer science concepts and building upon computer science and physical computing concepts around this very useful monster framework. And today we're going to get to project ideas and project options that are available for our very useful monster and how you may want to implement those in the classroom. But first, I wanted to start with just an overview of what we've done so far and do a quick recap of the key lessons we've learned so far, and then we can jump into the final project. The journey of our little monster has started from the simple program giving it a hello world, a beating heart, all the way through to where we are now, where our monster is ready to grow up and become part of a project. If you remember, the whole purpose of this very useful monster is to provide a framework that builds logically and in an authentic way and an engaging and fun way for the students to learn these computer science concepts and then take it further. And the key design principles that I used both in designing my products but in designing this curriculum are those constructivist design principles of low threshold and no ceiling to what you're doing. The low threshold is that at every step, trying to identify quick wins so that the student can quickly engage and work with it. And the no ceiling is that once you have a varied abilities among your students, and so you want them to be able to explore at their own pace beyond that first quick win. The project itself is what I call the wide walls. It is the wrapper, the framework within which the constraints really within which we want our students to be working here. And these are a very important part of a project because when I started in this, a lot of people would talk about this project they used to do in engineering school where you'd get a box of parts and you had to solve a problem with this box of parts and do all these things. And it was so open-ended and it had many flaws for this age group and for many students these days for a number of reasons. For one thing, with the box of parts, it presumes that the students know what to do with the parts and know how to even engage with the parts. The other thing is that there's a reality that a blank canvas is a very intimidating thing. And that's why things like Bob Ross kits are still popular. All they are is paint and brushes, but they provide a framework. They provide projects to do within there that may give you those quick wins, but also give you that opportunity to expand. But the walls in many of those kits, if we want to continue this analogy, is the fact that those kits are all about landscape painting. You're going to learn how to do trees and mountains, and maybe sometimes in the winter, but at the end of the day, they're all trees, mountains, and landscape. And those are the walls. But you can see within that, there's a lot to grow. And that is the goal of this project. And even if you choose not to adopt this project as what you do, I definitely suggest applying those three principles: low threshold, quick wins, no ceiling, give them an opportunity to learn a lot beyond that. But also remember, you need those walls. You need that framework. You need those constraints for the students. And that's what the goal of the very useful monster was. We then took our monster and explored what it could do with the microbit. After giving it its beating heart, we explored the fact that the microbit has lots of sensors built into it. And those sensors are very powerful and very rich just in what is built into the microbit. We have the accelerometer, which can be used to sense a force of acceleration in 3 axes. That same component can tell you pitch and roll of the microbit. There's also a magnetometer, so it can be used as a compass. It can be used as a way of sensing magnets or the proximity to magnets. There's a light sensor built in. There are lights built in. There's a temperature sensor built in. The microbit is incredibly rich in what it can do and what you can do just with the microbit and explore. And I would say the key takeaway as you explore or work with that, besides the fact that you can get pretty far with just the microbit and the board, or even just the microbit, but the big key takeaway I would say is remember to always know what units each of those sensors is working in, because they're all different. You have to know what is the number it's going to give me back and what does that number mean, and understand that. And you can look that up. There's always a little help. If you right click on most of the blocks in MakeCode, you can look up the help. And if you scroll through, you will see the units. But the units are critical in knowing what it's looking at and how it's giving you the data back so that you can then use it correctly in your code. And then on top of that, try to understand at a very high level, how is that sensor working? Because sometimes one device might be using multiple sensors. So for example, we talked about how the accelerometer, which senses the force of acceleration in 3 axes, is used to sense the pitch in the roll, to sense the angle that the microbit is staying at. Because when it is flat, it knows that the force of acceleration should be only straight up and down on it, and it should be close to -10 because it's a negative force down in the way the x, y, and z of that axis are. And when it's angled, that force will change and additional forces will be applied to the x, y, and z. So when it tells you the angle that it's at, it is because it is sensing a change in force and calculating that for you based on the force. Why does this matter? If you wanted to, say, have it track the angle at which you throw a device that has a microbit built into it, you're going to get a weird reading because that angle calculation is based on it being an object that's stationary, and the only force being applied to it is gravity. If you're applying additional forces to it, you're going to get weird responses. Other things like the light sensor use the LEDs, and so you need to remember with that the LEDs are tied to the light sensor, and you might get different readings if the LEDs are on or off, or even showing an image off of that light sensor, because it's using the same device to measure 2 things. Also, we talked about, even more in the weeds, but something for more advanced people to discover, is that the same clock that controls the motors, like the servos, is used to control the sound. And therefore, if you try concurrently playing sound and running the motors, you might get weird reactions and unexplained reactions to it. So, like I said, the key takeaways of playing with the inputs and outputs are knowing your units and trying to have a basic understanding of how it's working. In our last class, kind of went back to the inputs and outputs and explored buttons, and how buttons are a very rich and simple input and output to play with, especially if you want to start introducing external inputs to the sensors that are built into the microbit. We were able, with one motor, to just do 2 different projects with the microbit and talk about 2 different projects with the microbit. We talked about the chatbot, or the bot that can lip sync, and we talked about the Ticklebot project as another simple input-output project to explore with students, keeping everything super simple so that you can focus on understanding the code and maybe making a fun build beyond that. Getting back to the buttons, we use the buttons, or one of the forms of buttons, on the Ticklebot concept, and you can even see how it could be used in a chatbot concept, but using buttons as a trigger and exploring how buttons can work in fun and interesting ways and really are everywhere is important. And I would say the key takeaway on the buttons is buttons are super easy to make and can be built in very clever, unique ways for students to explore, and are a great introduction to inputs for them when doing physical computing. Once we explored the basics of inputs and outputs, we then start to expand our coding a little more and start to talk about functions and variables as ways of keeping track and memory. And it's funny that sometimes you get a little tortured when you are doing metaphors like this monster and what is a function? Is a function a memory, or is a function a reflex? Or you can decide what makes sense for you. But a function was a way of storing a block of code that, in this case, in the use of our monster, we were talking about that as blocks of code of emotions: happy, sad, hungry, angry, and coming up and creating blocks of codes that represented that for a monster and making it easy to reuse those. Variables kept track in a different way. They helped us keep count of things. They helped us keep a different form of memory, not as much of a reflex, but as a way of remembering how many times something happened. And we explored how using those helped us build a very rich Tamagotchi like pet with our monster. And the number of ways we can expand upon and push that idea further is one of the things we explored there. From functions and from that Tamagotchi, we took another step up to the radio. And I don't have a fancy little image here on my document of the radio, but the radio was a key communication. Oh, and one quick thing I wanted to say about functions. The key takeaway I would say about the functions is give them logical names and try to be consistent in whatever name structure you choose. As your code gets bigger, it's good to remember what you named that function for and why it's there. So sometimes students might get cute and be like, oh yeah, this is just come up with funny names for the darn functions and think they're being all clever. But then later on, as your code gets bigger, you don't remember what did Patooey do or what did Grumble or whatever do. It's good to keep consistent with your names. And that also was important with when we get to radio, because the radio, as we explored, gave us an opportunity to let these microbits communicate with each other. And that was rich in lots of ways. It could sense both proximity to other microbits, but also send information back and forth. And that's a great example of where naming conventions are valuable, because one sample you could even do is have a remote control that you design, that you have one remote and you're saying, okay, this is going to control your monster, and these are the codes, this is the instructions it sends, and then they have to write their code around whatever you tell them those instructions. And so that communication, knowing that when I want it to move forward, I'm saying move underscore forward, or move forward, all one word, or move capital F forward in the camel way. The underscore is what they call snake, if you really want to teach them what it's called out there. But the idea of having a standard and a known language within which to communicate is important, so that you can actually talk to each other correctly. And so with the radio communication, we covered a lot of how to do it, but also the same lessons from the function and variables, which is be consistent in how you transmit information so that the other side knows what it's getting and can use it. And just like any language, you have to have a known grammar and known spelling so that people can communicate and understand each other. That applies within your code and between it with the radio communications. And finally, last time we talked about the AI features and how to explore the AI features of the microbit using the code.ai blocks, and how it's all around using the accelerometer, how they've implemented it. And I would say the key lesson of the AI is to focus on the training design. It's the way Microbit has implemented their AI. The key lesson is really to think about how you train it is important to how robust your code is. So in the example we went through, if you only train it to look for two options, it's going to differentiate everything in the world against that filter of two options. Whereas if you train it to look for multiple options, even if we're only going to use one or two of those options in our code, it can be smarter and more discrete and more precise in how the code will work. And the way they've implemented it is very strong for that. Forgot the key lesson I want to highlight for the radio module. I would say there were two primary key lessons. One was the language and kind of the communication. But I would say the other is that remember that because these radios have the ability to use up to 101 different channels, you can use one remote or one device to control multiple other devices. And that gives you lots of opportunities in a classroom setting. That's the very quick recap of what we've done so far, because I really wanted to get to this last little corner of my little chart here, which is the project. Everything we have done thus far has been to use this framework as a way of teaching the CS concepts we want. And we've provided a little bit of flexibility for students to personalize it even within those frameworks. But the primary goal of what we have covered thus far has been to build foundational concepts. The next step is a project, is letting them get to the stage of taking their monster and making it useful and useful for them, and building a project that makes it useful for them. And this is a uniquely powerful framework that is very rich for this stage of the process, if you can believe it or not. It may seem like I'm force-fitting this idea into my very useful monster, but the reality is that these very useful monsters are an incredibly rich area for teaching design thinking and teaching problem solving for the students. And to highlight that, I wanted to just talk about how this is actually a track you could follow into college if you wanted to. And there are programs, and this is just based on a preliminary search, I'm sure there are many more, but at places like Yale, MIT, and many other colleges that actually go into this idea of personal robots, social robots, assistive robots, and do a lot of academic research and a lot of exploration of these concepts of how to take these robots and make them useful for people in the real world. Because they all lack imagination, they call them robots. We're calling ours monsters, but it's the same idea. We are talking about creating, ours are robotic monsters. It's just fun to call them monsters. But this entire world, which has large universities and some of the top universities of the world working on, and these is just a small sampling of them. So really want to highlight that what we are talking about of taking our monster to this next level and exploring what can our monster do is something that has a rich field of research behind it and lots of opportunities to explore and to discuss with our students. As a next step, I wanted to show 3 videos that highlight what there is. The first video is something we actually discussed a little bit, which is, this was from a Kickstarter. It was in 2015, and it was a person who was designing a robot-like object to teach better habits to people. And it's one of the things we talked about as what could be a logical thing for the next step for our little Tamagotchi pet is something like this. And so these are quick videos. Let's watch this.
We all want to be that person. The one who wakes up early, dives straight into a morning meditation, is super productive at work, drinks those 8 glasses of water, and always hits the gym. But let's be real. Living that life means building better habits. And our brains want to follow the ones we already have, not the new ones we're trying to cram in. But sometimes, all you need is the right nudge. Hi, I'm Kayla, and meet Modi, a smart companion for building better habits. We created Modi with a distinct purpose, to empower people to take those small steps that over time result in big impacts in our health and happiness. He's more than just a cute face. Modi is designed in the latest insights from both behavioral science and social robotics. When you place Modi in your home or office, every time you walk by, he becomes an instant reminder to keep committed. Each time you do your habit, Modi is there to help you track and celebrate your small wins, giving you that immediate gratification. The better you get, the more excited Modi becomes. But slack off and Modi might get angry, or sad, or stay purely encouraging. Modi knows what works best for you because he's connected to the web. He's constantly analyzing and evolving, so he knows how you're progressing, if you're at risk of falling off, and when to send the right types of nudges specifically for you. Compare all this to the same daily push notification you keep ignoring. Still, how can something so simple actually change your behavior? To tell you about how we form good habits, let's start with something that we're all familiar with, forming a bad habit. Ooh, cookie. Fundamentally, your brain needs three things to form a habit: a trigger, a routine, and a reward. When I saw that plate of cookies, I didn't even think about grabbing one. My brain immediately triggered me, and I knew that eating that cookie would reward me with its sweet, doughy deliciousness. Your brain forms good habits in just the same way, by completing this loop over and over again. Modi works by seamlessly integrating these three elements into your busy lifestyle. Modi himself is a trigger, more specifically what's known as an environmental cue. And by using Modi, your habit is already set up to be small, distinct, and actionable. Finally, Modi's celebrations provide an immediate reward. He makes sure that you feel satisfied and accomplished each and every time. And perhaps a bit guilty if you're not. Modi is the outcome of over a year of human-centered design and engineering rigor. We discovered that triggers and rewards driven by emotion are far more potent than numbers, lists, or alarms. Now, we're finally ready to release Modi straight to you. The only question is, what habit will you form? Modi can't help you magically climb Mount Everest or run a marathon overnight. He's there to help you do something more essential. Become a better you, one habit at a time. But we need your help. Please back us and be a part of bringing Modi to life.
So this super simple device here that you can see how it has been designed to do something very similar based on what we've learned so far, you can actually do with your Bit Explorer and Microbit right now. Almost 90% of what you saw Modi doing, you could imagine building with your functions, LEDs, inputs, outputs, logic loops, all that stuff. Now, the web connectivity and all that's a little extra layers, but a good chunk of what you just saw and what this Kickstarter was trying to accomplish, you can see how our robot can do that. It's even possible to take this further. And I think this next example is one I really like because you can see that this person actually took the almost exact design of Modi and took it to another interesting step, but took this idea of making a very useful monster useful for another very different purpose. And that is this Danielle Boyer, who is a indigenous inventor who has designed this robot called Scobot. And let's see what she says about what it's for.
Hello, my name is Danielle Boyer. I'm a Anishinaabe youth robotics inventor. I want to introduce you to the Scobot. It's a robot that you can communicate back and forth with in Anishinaabe-Moan. I started by documenting the language with my grandma, and then it grew to having youth voices. Listen, what language am I learning? Anishinaabe-Moan. Listen, what is thank you? Miigwech. Everything is developed completely in-house and was created to keep indigenous languages alive. Because when our languages are preserved, we can preserve the land. Estimates suggest only 50 languages will be left by 2050. And when you lose your language, you lose your culture. Everything is distributed through my youth-run charity called the STEAM Connection, and we actually distribute everything for free because I don't believe that indigenous languages should ever be sold. The robot itself is made out of a recycled bioplastic and is ethically developed.
You can see how there's a number of things. We've taken this basic idea of a useful monster that's basically a robot that we've dressed up, and she's taken it an extra level. She's found a problem, which is the retention of indigenous languages, and designed a way of using it as a way of teaching that. You'll also see there are other elements of her design that we've also talked about. This idea of, I would say she's Mr. Potato Headed her little Scobot quite a bit. There's different ways you can dress it up, and suddenly it changes in what it is. So this basic framework that she has taken and made it so that it's easy to bling it. And why do you do that? As we discussed, people feel more ownership and connection with it when they're allowed to personalize it and work with it. And I think Danielle has done a great job of doing that with this project. And I think she's a great example. It's an input and output. And frankly, it's not even a very complicated one with what she has in this current iteration of this Scobot. It's not even really using AI now. It's more like you talk to it and it responds a word. I think the half of her demos is mostly demoware with it, but you can get the idea and you can see how your students could build something very similar. I want to show a last video that is probably one of the more refined examples of what you can do with a very useful monster. And it's a well done video that talks through the possibilities. And it's actually used by our good friends. And it is the Aflac robot duck that they have designed. And this little video talks through the design process and how it was built. But you can see the steps of how this is not that different from what we've talked about. It's super simple design. There's a lot of talk about all the human interface engineering that they've done and this and that. But at the end of the day, the underlying technology is you could basically make this thing with your microbit.
What if we could make a change in the lives of children with cancer right now?
I was told that, I'm sorry, your daughter has cancer, and I was just in total shock.
Everything's really new in the beginning, and I have no idea what to expect.
Each year, more than 15,000 kids are diagnosed with cancer in the US, and the average length of treatment is 1,000 days. And so we thought about the need for emotional comfort for these children. And now we have the opportunity to bring the latest in social robotics into the field of medicine, bringing comfort and joy through this daunting process.
Oh, that's awesome.
What we try to do here is to give children the tools to understand what's going on and to empower them.
For our family and for Wyatt, the best use would be to help him communicate and a friend to comfort him when he's having treatment.
Play is natural to a child. Play is really how they learn and how they process.
So we leveraged play and some of the latest technology to create healthcare tools for kids with illness. Everybody knows the Aflac duck. We wanted to bring the Aflac duck to life into a caring companion for children with cancer. It responds and moves in a lifelike and natural way. They can feed their ducks, bathe their ducks, and when you tap these different cards to the duck's chest, it behaves with that feeling to help children communicate their feelings. By the time the duck is shipping, we will have spent 18 months designing, testing, and iterating with hundreds of families, doctors, and experts.
Hi, Levi. What do you think the duck is doing?
Singing.
Duck is singing.
Yes. Quack, 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 quack.
First and foremost, the duck is a constant companion for children throughout their treatment journey. Thank you.
Candy's going to do some breathing, and we're going to match her breathing. Just a tiny bit faster.
Perhaps most important of all, the ducks can share in the patient's experience.
Okay, actually, good job. Eli, look at this. Pack is also getting one.
Can I try?
Yeah.
What?
I think it's so awesome. You just feel comfort with something like that.
I really like the Aflac duck to be your friend, to help you get through all your tough times here.
I think the duck has the potential to have a huge impact on our patients, our families, and our healthcare program as a whole.
So technically y'all gonna make it happen to give everybody one or something?
That's the goal.
If she has something to sit with her, something that can take her through it. A friend that will always be there. And that would help a lot of kids.
I like it because it really does talk through the design thinking process. I don't know if originally designed or how you want to describe it, but it's a big part of the Stanford D School. And you can see almost every element of the design thinking process in that video. From the interviewing and trying to create empathy with the end user, to defining the problem, to going through ideas, prototyping and testing. You see every element of that. And the one problem with this way of drawing it is that it doesn't show that this is iterative. This is a process that goes around and around and keeps getting reused. And that video is a powerful way of showing the entire process at work. And for younger students, yeah, this is a big lift of a process, but I do want to show this framework because as you design curriculum and think about how you are going to evaluate and provide prompts and provide ways of ensuring that students achieve specific rubrics that you want them to achieve, I do think this is a good framework within which you yourself can place your rubrics that are age appropriate. Have the students done some form of empathy development? Have they talked to somebody else? Have they done some research into how understanding the problem and how others might work with it? How well have they defined the problem? This is an area often a lot of people jump to a solution. They like to jump to ideation before they define the problem. Having them write down a problem statement could be enough of the rubric for this to say, okay, what is the problem I am trying to solve? And write it down. That is an important step for them to take when they design this. What is the problem they are trying to solve? And what was their problem statement? And how would you think that is? And then what is your problem statement? And different people might come up with different problem statements based on watching that video, but that's a good discussion to have. But I do think it's important as you develop your curriculum and think of your rubrics, that you can use these frameworks as a way of like making sure you're touching upon every step of this. Age appropriate, of course. Then there's the ideate. Did they immediately say, this is what I'm going to do, and then backflow their solution into everything else? Or did they have different ideas? You want them to explore multiple ideas and multiple solutions. You don't want to just jump to your first great idea. Now, maybe your first great idea is what you end up doing, but you want them to have the discipline of exploring other options before they make just what they want to make. I want this to be useful for me for this, and I think that this is. Now, it could be a subset of it. Like I wanted it to, let's say it's something that is designed to give me good habits, and I'm going to use the accelerometer as a way of doing that. Maybe the ideation is where I carry my microbit. That maybe if it's going to be tracking, does it sit there and do I interact with it? That first video I showed, or is it something you wear like a wearable? And if you wear it, where do you wear it? And maybe the ideation is there. But you want to see some evidence of thinking a little bit of options. And for the older students, they're going to go much deeper. You want to see them throwing a lot of it. At one extreme, it's putting all these Post-its on a board. No idea is a bad idea. The ideation is often a very important part of this. But it could even just be, if you have limited time or younger students, just make sure they have the discipline of asking those ideas. The prototype is another important step here, where you don't want them to just jump straight into this linear path of building a final product. You want them to explore various options. And before they do their final design, did they do cardboard mock-ups? So one easy ways for younger students to prototype is to make cardboard mock-ups. Another one is to do storyboards, where you have them do it almost like a cartoon. What is the flow? How are people going to interact with this? And just by doing a really quick stick figure cartoon, that can be almost a prototype. Now, in the physical world, a physical prototype is incredibly important, and that's why giving them clay or cardboard or letting them build prototypes is important and valuable for them, because they interact with it and they see how it works. But finding a appropriate tool and then making that part of your evaluation, part of the rubrics for evaluating them, it's important to have that prototype. And then the test is always important, because what do you prototype for? You prototype something to then put in front of people to interact with them, and then you go back and you observe and you do the entire process again. Now, often the empathy and the defining the problem and the ideation is not fully iterated. You're iterating between the test and the prototype a lot, but the empathy is a critical part of the prototype evaluation as well, because you have to observe, you have to watch people and understand, okay, I thought this was going to happen, but people didn't react like that to it, and therefore I'm going to do this when I do that. You don't want to ignore those in that iterative process. You want to explore that and keep those within your rubrics. Definitely want you to think about this design thinking framework even at the graduate school, at the D school level, because it does provide a good framework for your rubrics and for your own evaluation of the project, what you give them, and how you evaluate and see what they do. Because I recognize that the D School is within the Graduate School of Engineering at Stanford, and this framework was designed to teach students there how some of these elements may feel a little more challenging with younger students. I wanted to provide two other resources, or let you know about two others. And the primary one is Project Zero at Harvard. Project Zero is the Harvard Ed School's version of the D School and with their own flavoring. But one of the things that they have, this website that I provided the link for, that provides all these kind of thinking routine toolboxes. And they provide a whole series of routines and very discrete steps and projects for doing this. This is the Project Zero website from the Harvard Graduate School of Education. And they have this toolbox that has a lot of options and links. And the previous slide that you didn't see was that the next slide from the D School had two links, of one from IDEO. IDEO is a professional group that implements a lot of these things, and then Project Zero is the Harvard group. The Project Zero routines toolbox, lots of little projects within here along different steps of the process: core thinking, introducing. And they do have some projects in here that are specifically designed for grade school and elementary school children to build the competencies in these thinking skills. So they have taken these ideas and put them into frameworks and worksheets and things that help you take that further. And one that I particularly like, let's see if I can find it. It's within their introduction and exploring ideas, is this parts, purposes, and complexities. If I click on that, you'll see that this activity, it has different ages: preschool, elementary school, middle school, high school. They've got modules and examples of how to do these processes at different ages. And you see the link resources here for younger children. Here's a little PDF that will talk through the process. And I like this one for what we're doing because it's a great intro framework. It's easy to take an object, break down its parts, understand its things, and then you can figure out how to interact with it. So it dovetails very nicely into this project, because once we understand how other objects work, we can go in there and interact with them. And so saying like something as basic as a switch, you could do a parts, purposes, and complexities. You could take a ballpoint pen apart and understand what the mechanisms, have them go through this. And so I think that a lot of these steps in here, if you want to deep dive in the learning process and in the problem solving process, the website at Project Zero provides a lot of really good opportunities to do that. IDEO has some items as well, but really I think the Project Zero is a very strong resource for that and what we're doing. So those are the two big ones. And from there, I wanted to just open it up to a discussion and talk about the different options we have and ways of taking to that final project phase, and how that project phase is so rich in future possibilities. Your students could end up studying this in college. This could be what they do in college, is actually building a very useful monster. When we think about creating authentic problems that might have relevance, there are grad level tracks out there that explore these in greater detail, but they're also accessible to the students because those same principles, those same ideas can be introduced to younger students. And that idea of building habits, that cycle, just showing that simple thing. It's what is the trigger, what is the reward, and what's the behavior we're trying to get, and how do we encourage this cycle to happen over and over again? That's something that they could build right into their Tamagotchi pet, even at middle or late or grade school, and explore further. If you have access to a bigger design lab, or you can go deeper in the prototyping and making it look better. But even just by Mr. Potato Heading your robot, you can get pretty darn far with them. So that's the arc that I wanted to discuss, and didn't want to ramble too much.